Okay, well, there are two main properties of determinants. Determinant of a product is the product of the determinants. The determinant of the inverse of a matrix is a reciprocal of the determinant of that matrix. Now you might ask, well, what if the determinant of the matrix is 0? Well, one thing, if the determinant of the matrix is 0, you exclude it. But if the determinant of the matrix is 0, it's not going to have an inverse. Okay? Determinant of the matrix 0 means the matrix can't be inverted. Okay? Now one thing I haven't stated, but it's implicit here, is these are always square matrices, n by n matrices. Determinant is not defined for a matrix that has more rows than columns or vice versa. Okay? In those matrices, in general, represent transformations from Rn to Rn. Okay? Or equivalent spaces. Okay, well, there we have it. Now, this one's pretty straightforward. Okay? Let's see what this means in terms of if you have a matrix that factored into elementary matrices, right? Well, if A is a product of elementary matrices, I'm going to write that as a product from I equals 1 to m of the determinant of E sub I. The pi there stands for product. Pi starts with P, product starts with P. It's like a sum, except now you multiply them all, right? It's just saying I didn't have room to write determinant of Em times determinant of E, okay? And since multiplication of real numbers is commutative and determinants are real numbers, doesn't matter if I write this from I equals 1 to m or from I equals m down to I equals 1, right? Does that make sense? And that is handy. I think I don't know, remember if I said that on tape or not, because the determinants of elementary matrices are very simple. And I think I said it on tape, but just say it real quick. If you multiply a matrix, if you take the identity matrix and multiply one row by a number, the determinant is that number. If you add a row to a multiple of another row, it doesn't change the determinant. I mean, the determinant is 1, okay? Determinant of the identity is 1, it didn't change, so it's still 1. And if you interchange two rows, the determinant changes sign. Determinant's -1, okay? That can all be proven from these rules here. Very easy to do. If you were to switch two rows, what would that do? Well, among other things, you could then do the expansion on the second row, which is the old first row, right? But because of the -1 to the I plus k, the second row starts with a negative, then a positive, then a negative, which is going to give you the negative of what you had when you had the original. Maybe you understand that, maybe not, but it's that easy, okay? And if you go back to the tape here, or the tape, the video, and listen to what I said 6 or 7 times, it might become clear to you, okay? So, very handy. And that's how you do determinants of large matrices. You don't do this, which gets totally out of hand very quickly as your size of your matrix gets bigger. Okay?